So a while ago, so I'm from the Netherlands, and a while ago there was a heat wave in the Netherlands. So it was very hot in our rooms, and I have 3 children, teenagers, and they were complaining. Their room was very hot, way too hot, as they said, and they asked me, "Hey, can you do something about this temperature?" And of course, you can immediately buy an air conditioning or something. But I thought, wait a minute, I'm a geek. So no, wait a minute, I'm an engineer. So I have to measure first. But there also comes in the geek part, because I could buy some temperature sensors and use it in a fun way or in a useful way. So I bought some temperature sensors, put it in their rooms, and connected those temperature sensors to Home Assistant, which is a home automation platform. Any Home Assistant users here? Good. So you know what we're talking about. So I connected those to Home Assistant and gave my children access to Home Assistant. So then they could see what the temperature of their room was. Turned out, only showing the temperature data to them was already it solved it almost, because now they could say, "Oh, I have the hottest room. It's the worst for me. It's terrible." But then they are like, "Okay, it's the worst for me, so solved." Kind of. So I still had the temperature sensors, and I thought maybe I can do something useful with it. So I started doing some coding exercises, coding katas based on the temperature data. So I did it in Java as a Java engineer, of course, and started to doing some playful code examples, just to experiment and practice my coding skills. But at some point, I run into some things that I could not really do because I was using streams and a bit more streams because I wanted to practice that. But at some point, I was like, hey, I could use some more from the streams, which is not there. And of course, I can do it in another way. But yeah, so then I abandoned that kata for a while. And then this last March, Java 24 came out, and Java 24 has a feature which is called gatherers, and that's the topic of today. And it also solved the things I was running into. So that's what we will look into today. So I already explained that I have children, and you know they're teenagers, but I didn't say that much about myself. So who am I? My name is Hinse Schuur. I'm from the Netherlands. I work for a consultancy company called SDB Java, and I'm a software engineer, mainly working in Java, but I also did some projects in Scala. So I'm also used to some functional programming stuff, and I worked in different industries as a consultant. So who of you is not using Java? One. Okay, wonderful. So everyone else knows Java, and everyone else knows streams, right? Java streams. Okay, cool. So a quick recap. What are Java streams? So those are not to be confused with reactive streams or something. These are just functional views on collections. So if you want to do some functional transformations on a list, that's not something you can do. You need a stream for that in order to make those functional transformations work. The nice thing about those streams is that you can have chains of small transformations. So you only need to think about this small, tiny transformation and then put them together. And when the streams were released, which is already a while ago in 2014, which is 11 years ago now, those were also a nice fit for the lambdas, because lambdas were introduced in Java 8 together with the streams. So the lambdas that you could use were very useful in this stream context where you wanted to do a filter or a map. And also interesting to know about the streams is that they are computed lazily. So if for example, if you're not working with a stream, but with a list and you want to have a transformed list, you need to go through every element, transform them first and then filter it or some way. But at every point, it does all the computation. While with streams, you can have lazy computation. So it doesn't have to compute everything, only the stuff that you need, actually. And streams can potentially be unbounded. I don't think we will use it a lot, but it's good to have it. And when it was introduced, it was also promised that it was fairly easy to do in parallel. You just do the parallel stream, and you get parallel support for free. Are there people using parallel streams a lot? Not too much, yeah. I think most of the people just use sequential streams. But if you need to use it, it's very easy to use to do so. So, quick recap: what is a stream pipeline? So essentially, it's a source of elements that's emitting elements one by one, and then you have any number of intermediate operations, and at the end, you have a terminal operation. And intermediate operations are things like map, filter, flatMap, map multi, those kind of things. And the terminal operations are the collect, which in the beginning you had to do collect and then collectors to lists, for example, to get a list, or you do a for each. But important is that you need to call that terminal operation in order to have your stream do something. So there might be some people, or you might have a friend who at some point forgot to add the terminal operation while you were debugging, and you couldn't figure out why your intermediate operations weren't triggered, or whether you couldn't see any debugging output from the intermediate operations, but you forgot about the terminal operation. Could happen, especially when debugging, right? So in production, you won't forget it. And the terminal operation is kind of the moment that the stream jumps into action. So it's also a bit comparable to what I have with my teenage kids. So if they're upstairs and I tell them, please put your laundry in the box and bring the dishes down and clean up your room, nothing happens until I perform that final operation, the terminal operation, say, do it now. And then they start doing it. But the same thing with streams, which is also true for them. If next day I say, do it again, they say, wait, what? What did I need to do? And that's also with streams. You cannot reuse them. You can only use them once. And as soon as you call the terminal operation, you have to create a new stream to do stuff. Oh, that went too quick. Yeah. So if we take a quick look at a demo, we all know how streams look like, but it's good for the example. So I created a measurement stream, which is an example, which delivers a stream of measurements, and it gives temperature, sensor data. It's artificial data in this case, and it will give measurements for every minute. So if we look at the measurement record, we see a timestamp, which is we see the temperature and a sensor ID. We will mostly be looking at temperature for these examples. And good to know that this is an infinite stream, and that's just for the example because I wanted to experiment with infinite streams and how you could handle them also with gatherers, which we'll look into later. So if we look at an example, here we have we create a stream. So this is the source, and then here we have the intermediate operations, and we have the terminal operation for each. By the way, is it readable enough in the back? Good, I see nodding heads. I think everyone is still awake as well, so that's also good. No after lunch dip yet. So if we look at the stream, in this case, we filter by temperature above 20 degrees, and then we map them, every item. We format it in some way, and then we want to limit it, just have 50 elements. And here we also already see the laziness because it will at max map 50 items because the limit says limit 50. So even if the measurements stream is infinite, it will only map 50 elements. So I put a breakpoint here because I also want to showcase something if you debug this. So I can first run it. So as you would expect, it gives some nicely formatted measurements. So the output is not rocket science, but yeah, this is what we will get. But the interesting thing, and there was only a thing I discovered when preparing for this session, is that there's some interesting debug utility in IntelliJ. So if you put a breakpoint somewhere in the stream, doesn't have to be at the source, you can also put it at a step further, and you do a debug operation. IntelliJ gives you a nice option, which is located here, and it's called Trace Current Stream Chain. And what it does, it shows the steps in the stream. So so here we see the source on the measurements. That's the elements coming out, so I can inspect them one by one. Then I see what the filter operation does. So I also can see how this element came to be, where it originated from, so what element it was linked to. And I can also see the mapping operation. So if we look at here, we have a measurement, and then apparently we did a map operation, and now we have a string here. So this can be very useful. In this case, the stream was very simple, right? It's not too hard to visualize what's going on, but this can already help. And if you have a bit bigger monitor or maybe a curved screen, you can also use the flat mode and have the whole stream chain in one view. So already people using this view while debugging? 1, 2, 3, 4, just a few. So at least you learned something today. So good, make notes of this. Yeah, so we can continue this example. It will output the same data, of course. So far, everything fine with streams. So I could do the temperature data, I can do filtering and some formatting. So it's all fine. But yeah, I was missing some intermediate operations because I wanted to do some windowing functions, which we'll also look into a bit later. But there were also other people. I was not the only one who missed some things in stream. So people complained about, hey, I would like to have something like a fixed window on a stream, and then maybe with an argument. Or maybe I want to call something zip with index. Or maybe I would like to only get every 5th element, right? So that's not something you can do with a filter, because with filter you can only look at the current element, but you don't have access to index or something. So also something like every 5th element or every nth element doesn't exist on streams. So that's a bit of a bummer. And then the Java team thought, okay, how are we going to solve this? We can add all those additional functions like zip with index, like every blah, blah, blah. But that will largely increase the streams API. And there might be parts that no one ever uses, and there might be parts that a lot of people use. So we're not sure. So therefore, they invented a generic mechanism, which is called gatherers. It's kind of like the collectors, like we have for the terminal operation, we have collectors there, which is also like pretty generic. But yeah, for this they had to come up with a new name because collectors was already taken. But this is still, it's kind of collecting, so they looked for a synonym and they ended up with gatherers, which is a generic mechanism for intermediate operations, available since Java 24. So it's also part of Java 25, which came out recently. And it's as simple as calling gather with some gatherer on a stream, and that's how you use it. And it's heavily inspired by collectors. So if you ever implement your own collector, then this might look very familiar. There are some small differences, but it looks very familiar. But I can imagine that not a lot of people implemented their own collectors, or at least I didn't do that until looking into gatherers. So what are important to know about gatherers is that they support parallel streams. So we had the nice parallel for free paradigm, but with the gatherers that's also supported, and they also thought that very well through. We won't see a lot of parallel streams today, but yeah, it is supported. It supports the lazy evaluation, which is also important if you consider that you can have infinite streams. And the important bit is that you can use state. Previously, with intermediate operations, with a map or with a filter, you couldn't really use state. You could have a map thing that did something with state, but there were no guarantees about what would happen with the state. And especially if you went parallel, then it was really hard to do state. And it was really not meant to use state. But gatherers, they explicitly support state, and the stream mechanism makes sure that the state is used in a correct way. And with gatherers, we can do many type of mappings. We can do one-to-one element mapping, one-to-n, n-to-1, n-to-m, n-to-everything. So you can basically implement every intermediate operation with this. If we look at an example, so we're looking at some temperature data. And on the left, you see the raw temperature data. It's plotted for, let's see, 24 hours. So it's quite jagged. It's not a very nice graph. So I thought I would like to have something like the average temperature per hour, like we have here. So like on 6 o'clock, it's, I cannot read it there, 18.5. And an hour later, the average temperature was about 20.5. But now it's, so per hour, we calculate the average. And then it's way smoother, I would say. And it's more clear how the temperature evolves. So we can use gatherers for this to do exactly calculating this average per hour. And for that, we can use our first default gatherer that we look at today, which is the window fixed or the fixed window gatherer. And it will go over the stream with a window size. In this visual example, I'm using a window size of 3, so 3 elements at a time. And what it does, it gathers the first 3 elements and then emits those to the downstream, like the next intermediate operations, in a list of 3 elements. So that's a window, which is a list of 3 elements. And the next element it pushes downstream is the next window. So it jumps that window size. So it's like jumping over your input stream and emitting lists of items every time. And for the last one, because that one doesn't have 3 elements, you will get a list of just a single item. If we see this in action, let's hide this one. So suppose we want to calculate the average of 1 hour. So we have the measurements again. We extract the temperature with this. We can do the gather. And we can use the gatherers dot window fixed. That's the default gatherer to have this. And we specify the window size. So in this case, if I want to have like an average per hour and I get the measurements every minute, I need 60 minutes or maybe 59, depends on how you look at it. So let's do it simple and have 60 elements. And as you can see, we get a stream which contains lists of doubles. So in this case, list of temperature items. This is already the gather, and then we can, in order to calculate the average temperature, we can use those windows that got out of it and calculate the average. So I create a utility to quickly calculate the average for that window. It's called a single window, by the way. Window calculates an average, and we can get that as a double. So now if we put a breakpoint here and we debug this one, we would see that it would calculate. So if we can take a look at this one again. Trace current stream chain. Let's go to the split mode because I don't have that much window space. So this, we have the temperature that we extract, then we do the gather. And here you see that the IntelliJ loses the connection between the input elements and the output elements. And that's because the gatherer can use some state, but IntelliJ doesn't know what it keeps in state and when it emits those items. It's not like connecting the dots. So it makes sense when we look a bit more in depth into the gatherers later, but it's important to note. But at least we can see now, if we look at the next operation, we get windows of 60 elements. So here, this one has size 60. So 60 elements, that's one window. I'm calculating an average on that, and that is, in this case, 19.025. So if I let this continue, I get the averages per hour. Of course, I can do some nice formatting. But this is essentially how this works. So that was the window fixed default gatherer. But there can be another way to try to smooth the data. Because here in orange, we see the temperature over an hour. Actually 2 hours, but you see it like jumping up and down. It's not like a smooth graph. So if you want to have a smooth graph, you want to do something like a running average. Like you calculate, at each point you calculate the average of the last 3 items. And that creates depending on what the running average is, whether you use 5 elements or 3 or 10, it creates a more or less smooth line. So we could use the sliding window for that, which is very similar to the window fixed default gatherer. But in this case, as you might have guessed, it slides. And each time it emits 3 items, or in this case, window size is 3, so it emits 3 items. But it does it by sliding over the window. So you can look back basically n items. And we can use that to calculate that running average. So if we see that in action, we take a look at another example. There we go. So it's basically using the same. So we're calling the gather method, which is our way of activating the gatherers. Dot window sliding. Let's do a running average of 3 items. And then again, we just have to calculate the average of that thing. So quickly took a shortcut by copying that code. Let's hide this. Man. What am I doing? Okay. So we have this, again, here we see the windows that we get. So it's a stream, a list of doubles, and then we calculate the average on that. So if we run this, we get the running average, and you can already see it's a bit more smooth. So 19.3, 18.6. It's a bit smoother than it was before. So this was the second default gatherer. In total, there are 5 default gatherers, and we will take a look at the others. So suppose we want to calculate the ongoing average or the cumulative average. So at each point, for example, if you're here, I want to know what the average was of all the previous items. And at this point, I want to know what the average is of all the previous items. So for that, we could use a gatherer called scan. And scan basically, again, goes over your stream, but it has an initial element and can use that to combine stuff. So you give the initial element and a scanner or a combiner or whatever you want to call it. And what it does, it takes the initial item. In this case, in this example, I'm using 0 as an initial item and using scanner to be a plus function. Of course, you can have other functions, which you will see in some coding example. But in this case, the first element is 20. So it looks at the initial element, which is 0, adds them together. And that's what the gatherer does, the scanner function. It adds them together and it emits 20. So it emits 20 downstream. For the next element, it sees 20.5. It takes a look at the previous value and combines those. And it adds them together, in this case, because the scanner was addition. And then so it combines it. And every time it calculated that new value, it pushes that value downstream to your next operation in the stream. So that's how it goes through the stream. And this is the scan. But there's also something similar, which is called a fold operation. Which works exactly the same. The only difference is that this one doesn't emit the intermediate values. You can see those are a bit lighter, so it calculates those intermediate values, but it won't emit them until the very end, when the last item has been emitted. Then it actually emits one value downstream. And you might recognize this as, hey, this looks a lot like something we already had in our streams, which is called reduce. Very well. So this is kind of the reduce, but yeah, as an intermediate operation, that's it could be an advantage, and it has some what was it more guarantees about order. So it's strictly fold left. While with the reduce, I don't think there's a strict order that goes from left to right exactly. So there can be some parallel things in between. So we could use this to calculate the cumulative average, as I mentioned. So if we take a look at an example, so suppose I have 60 elements and I want to do the scan gatherers.scan. Scan. I'll start with an initial element. And I want to calculate an average temperature. So in this case, I would need some thing to hold the state, because for an average, I need something like a count and a total, like this. And then for the scan, I have to create an initial state. So the initial value is a new stats object, like this. And then I need a way to combine it. So we have a function that has a stats and gets the new element and specifies how to combine it. So we return a new stats object, which has count +1, and it has the stats.total plus the element. So we're basically constructing something that keeps track of the count and total. And then at the end, and of course, this one needs to have some initial values. And now we have a bunch of stream of stats object, and now I can use them to create averages. So I can do some simple map and do something like stats.total divided by stats.count. And I'm not thinking about the 0 case because, of course, if you have 0 elements, then it will blow up. But in this case, I have more than 1 element, so it will work. So if we debug this, or if we run it, we see the average building up. So in the beginning, it's a bit jumpy, but at some point, it converges to roughly 19 as an average temperature. And if we want to just get the last element out, we just change this to a fold, and then do it like this, and then we get only the final element. So that's this is basically the average of all the 60 elements that I have for this thing. And then, so we had 5 default gatherers right now. There's a 5th one, which is map concurrent. Yep.
Sorry, quick question.
The
initial value was not used
in the example, you mean?
Yeah, that's 0, 0.
Yeah, so it passes this initial element as a first step. It passes it here. So I use it then to get the old value, stats count, and stats total to increment in this case.
Before you did the fold, it starts with 20, not with 0.
Yeah, that's a good one. Yeah, so so the remark was that it didn't start with the 0 element. So if we look, now I lost in the slides. Go up, scan. So here you see that with the scan, it doesn't emit the initial element. So if there are no elements in the stream, you won't see any element. And that's different from the fold. So the fold, even if there's no element, will always at least have that initial element. And in this case, this one never emits the initial element. So only if there are really elements, then it combines those. But good catch. But that's indeed the color coding of these examples. So the 5th gatherer, the last one, is map concurrent, which basically is a map, but then concurrent, as you might expect. It's using virtual threads under the hood, so you could use this to do some I/O work, or you could do a REST call for every element, which might not be the best design, but at least you could do it. And the thing that the gather and the streams guarantee is that you will get the elements in order as a mapping result. So for this example, I'm looking at a max concurrency of 3. So it calls the mapper for 3 items in parallel or concurrent. And when the first item gets mapped, so for example, it does a REST call and it gets back a result. So it immediately emits the first result. But suppose the 3rd element comes back first. So it skips the 2nd element, or the 2nd element is still waiting or working. Then it waits with emitting this element. So it keeps this element. And only when the 2nd element comes back, then it emits the 2nd and the 3rd element. So the map concurrent ensures that the initial order is preserved and that you will see those items in the same order, although the mapping happens concurrently using virtual threads. Yeah, so for a demo, there's not too much to see because it's actually map. But then we have this max concurrency thing added. So I'll quickly jump to the situation where the default gatherers might not be enough, because we have 5 default ones, but it's easy to think about problems where this might not be sufficient. And in that case, you can implement your own. So an important concept when implementing your own gatherer is the downstream interface, which you don't have to implement, but it's provided to you. So you can use it to push elements. And when you push elements to it, so it's more like to push elements to the next thing in the stream, it returns whether it would like to receive more elements. And this is a nice thing in those streams that it communicates that. And you can also ask it upfront or at any moment in time, actually, to see whether it's actually already rejecting. For example, if you have a limit somewhere downstream, after the limit. So if you have a limit of 50 and the 50th element has passed, then the is rejecting will return true. So then the stream mechanism can shortcut on that. But if you look at the getter, it's an interface with some types, of course. I can expand the types to make it hopefully a bit more clear what's going on. So a getter has a type of input elements. It has a type for the state, because it needs to know what state it needs to create and to pass later on. And a type of output elements. And it has some functions that it uses. So first thing is, if you want to use a state, you need to implement an initializer for that state. So here you see why the type parameters are there. And then the meat of the getter is basically the integrator, which integrates current state, input, and delivers some output elements. And we'll take a look at the integrator interface in a bit. And we have something which is called a finisher. And that gives you the opportunity that to, given the state, at the end, when the stream is fully handled, emit some more items if needed. So you could imagine, for example, with the fixed window that we were looking at before. So a lot of those fixed windows were 60, 60, 60. And for the last bit, there might be just 4 elements. And then the stream ends, but it didn't get to a full window. But it still has that 3 elements, for example, in its state. So when that finisher is called, it can still emit those items, those final 3 items, as a small thing at the end. So sometimes you need to do something at the end. It's not for all gatherers, but those fixed windows, for example, need to have this finisher. And there's also a blank spot in this because it's for parallel operations. So if you want to have like advanced support for parallel, you need to implement a combiner. But even if you're using parallel streams, you can still use gatherers which don't have like the advanced parallel support. So you can use sequential gatherers in a parallel thing. Then we have the final interface as promised, which is an integrator that integrates state, an element, and also has that downstream where you can push elements to if you need to. And if you look at the flow, this is what the stream mechanism does. If there's a gatherer, it creates a state using the initializer. Then for every element, integrate that state, and you can, in the integrator, emit elements. And as soon as all elements are processed, or there's something rejecting and the stream has ended because of that, not because all elements are consumed, but because there's some downstream rejecting, it will eventually call the finisher, and in which you can also emit those elements. So if we, and it's normally recommended to not implement your own interface, to not implement the interface yourself as a new gatherer, blah, 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 blah. But you have functional interfaces which you can pass method reference to, or lambdas. That makes it fairly easy to quickly create some gatherers. So we have all kinds of flavors with just integrator, something with initializer, so we want to have state, and for the things where we don't have state, it's a state void implicitly. But yeah, use the off sequential if you want to use sequential gatherers, and if you want to go for the advanced parallel support, you use the gatherer.off, which gives you the parallel supporting gatherers, and then you have to, if you have some state, you have to provide a combiner. So if we see this in action, so suppose, what happens with this? Like this. Suppose we have, which one was it? This one. So I already mentioned the zip with index. So suppose we have elements with in a stream, so like temperatures, 20, 90, 19, 18, something like that. But we want to prefix it with an index. We might want to do something like zip with index. So we would like to build a gatherer that does zip with index, which would give an index and a temperature, combines it to a new value. So this is something I can define. Of course, there can be libraries that provide this zip with index. You can build those libraries internally. Maybe there are some nice ones external. So I already created a factory method for that, which is also kind of recommended to build factory methods for your gatherers. So if we want to implement this, we start with a sequential gatherer. Gatherer.sequential of sequential, And in this case, we need some state because we want to keep track of the index, right? We want to do the zip with index, so we need to keep track of the index. So we create a state class, which we can do internally here. We don't want the state to be leaked outside, and we can just give it index, something like this. Oh, yeah, and also good to know is that here for the state, I use a wildcard type identifier because for external, it should not be relevant what the output, the internal state is, right? The state is only used internally to combine the integrator and the finisher, for example, so that it knows which type to use, but externally you don't need to know what the state is. So for the sequential getter, I first need to have an initializer. And in that initializer, I will just create a new state object. And the nice thing about the state is that the streams mechanism will make sure that it passes the state at the right moment to your getter. So you can just, it's mutable state, you can just mutate the state. So we have an initializer and we need to have an integrator which gets the state element and downstream, state element and downstream, and it does something useful with it. In this case, we want something, we need to create an element, right, in which we want to use the zip function, in which we can use the index. So what we can do, we can create a new value, and we use the zipper for that. So that's the function that we got. And we give it the index, but then we use the index from the state, but we can already increment it. So we can mutate the state. That's a nice thing about the states here. And we apply the element that we got. So this one. So we calculated a new element, and now the only thing that we need to do is push this element to the downstream. So we push that new value to the downstream, and it's still complaining about something. No, this one. So the integrator needs to return a value, whether it accepts more elements or not. So that's that rejecting part. So I could do, say something like, okay, return true. I can use more elements, but what we could also do is return the value from this downstream, because that also indicates, hey, I want to have more elements. So if there's now something, a limiter, for example, downstream, we will automatically propagate that. So a lot of times when implementing getters, you can just return downstream.push. So that's just a shortcut for some things. And we can probably inline a bit more to make it a bit shorter. But if we, so basically this is a simple getter using some lambdas. So if we run this, we'll see that it actually prints the index and then the value, the index and the value. So this is a very basic getter. And you could think of more getters. So I lied to you when talking about the sensor data, because the sensor data in reality is not per minute. As some of you might know, you only get the temperature updates when it changes. So the fixed window doesn't work to calculate the average temperature per hour if you use real sensors, because you don't get that data per hour. But then you get a timestamp. So you maybe want to do something like a window by, where you look at some, okay, what's the hour in the measurement, and then you can use that to make windows of an hour, but they are not like 60 elements. It could be 1 or 4 or 5 or 10. So you could implement your own window by to do something like that. You could implement a simple getter. So if you want to experiment with a simple getter with state, you can, for example, implement an every. It's a very simple thing. You keep track of the index again, and you can use it like every 5th element. That sounds like a nice idea. So what did we gather today? Because I think we covered almost everything about the getters, or most of it that it's useful to know about. Getters are collectors, but then for intermediate operations, there are 5 default ones: the window fixed, window sliding, scan, fold, and the map concurrent. And if you implement your own gather, prefer the factory methods to like the off sequential and the gather rod off, but also offer a nice factory methods for your consumer. So if you're creating a reusable gatherer, provide a nice static factory method to create those gatherers. Hide the internal state, like I mentioned, with the wildcard type parameter. And always try to start with a sequential one. Don't focus on the parallel one immediately. Start with sequential. It will help you a lot. And only if really needed, you can look into parallel support. So I think that basically covers everything about the gathers I wanted to share. But yeah, that didn't really help my kids because their rooms are still warm. But yeah, at least my streams got cooler. Well, thank you. Are there any questions? And otherwise, I'll be around so you can. Oh, there's one question. Although I think we're over time, kind of. But okay, yeah, you can always come. Okay, yeah, cool. Thank you.